Welcome to All Week in Astronomy. This week, an apology. You see, a couple of weeks ago I had a rant about an impossible black hole. It was for a paper called A Wide Star Black Hole Binary System for Radial Velocity Measurements, recently published in Nature Astronomy. The crux of my rant was that the paper itself put out a few possible ideas of how that black hole could have formed. So it wasn't necessarily impossible, just relying on a very unusual situation for it to form. And in a galaxy with hundreds of billions of stars, unusual situations still happen. We don't need to yell impossible when we just mean it doesn't fit with what we expect. I still think the idea is valid, however I apologise for missing another possible explanation, which I really should have noted. The paper just might be wrong. Wrong results get past peer review often, and while Nature Astro is generally pretty good, no system like that is ever perfect. Sometimes wrong things get through. So since the paper was published, a few things have come up on arXiv arguing this explanation. As a quick reminder, arXiv is a library of preprints, academic articles which have been written but not yet accepted for publication. I'll use one as an example. It's called Not So Fast, LB1 is unlikely to contain a 70 solar mass black hole. It was submitted for the monthly notices of the Royal Astronomical Society by Karim El-Badry and El-Quataert. I'll go through their logic to show why they're calling into question the earlier result. So firstly, they set out the claim as a paper in the introduction, saying the spectrum of LB1, which is the object they're studying, contains both the expected absorption lines of a B star and a strong H-alpha emission line, which the authors interpret as originating from an accretion disk around the black hole. So you see, if you plot the intensity emitted of light by a star against the frequency of that light, you get a spectrum. Some emission being broad, for example black body emission, some line features, or features at very specific frequencies in that spectra, which are known as absorption and emission lines. Absorption from light being absorbed, emission from light being emitted. H-alpha is a very specific emission line where the electron in a hydrogen atom drops from its third orbital level to its second, releasing a photon. The opposite can also occur. H-alpha absorption, absorb a photon, raise the electron in the hydrogen atom. So the first part of the original paper is correct. They used good scientific reasoning to deduce that the companion star had a minimum mass of around 6 solar masses from the radial velocity of its companion. They could use that to rule out some options on what the companion could be, pointing out that if it were a main sequence star we would have noticed its emission. They identified the spectrum from the system as that of a type of star referred to as a B star, and then some more questionable analysis happens. They argue that the H-alpha emission comes from an accretion disk around a black hole and attempt to deduce the mass of the black hole from variations in this line. You see, they measure a wobble in where the emission line is in terms of frequency, and because Doppler effect frequency changes come from velocity changes of what's being moved, they attempt to use this to give you some indication of the motion of the black hole, because this accretion disk is moving, in their idea. As the black hole and star orbit, the emission line moves. However, there's another explanation which is pointed out in this letter. You see, in brief, B stars show absorption lines of H-alpha, and in a similar way, those absorption lines move as the B star orbits its companion. This means the observed H-alpha flux is a combination of the effects of emission and that absorption. What the letter says is, if one wishes to determine the velocity of the H-alpha emission alone, it is necessary to first account for the wavelength-dependent reduction in total observed flux due to the absorption line. Yeah, you need to account for this absorption by the B star. And the letter does a rather beautiful demonstration to this. I'll link it in the description if you want to see, but essentially they model a stationary emission line and the spectrum of a B star, like that in the original paper. They then shift the stellar spectrum due to the motion of the star. They focus on the H-alpha emission line and show that that shift causes what seems to be a velocity of the H-alpha line, which would suggest a large black hole, despite the fact that by design, because they created this as a stationary emission line, their data had no such movement. They then go through data from the Keck high-res observations of the system, which were the telescopes and equipment used in the original paper. They show that a proper correction from this absorption effect makes the radial velocity motion disappear. In other words, no massive movement of emission lines, therefore no giant black hole. Another preprint from a team of researchers led by Abdul-Masih of KU Leuven also pointed out the same problem. They use a slightly different method. They gather observations of LB1 using a piece of equipment called the Hermes spectrograph. which is on the Mercator telescope in La Palma. What they aim to do is isolate the actual H-alpha emission by subtracting an absorption model of H-alpha based on the observed parameters of the B star. They then create H-alpha profiles using that emission and some phase-shifted absorption, and essentially try to recreate what the original authors saw in their paper, which they do. Quick point, these are still preprints, they've not quite yet gone through peer review. However, it's worth mentioning them as they appear. Both these groups of scientists came to the same conclusions about the error in the paper. And if you like, this work by other scientists writing on papers that they've seen is in effect the second and more important stage of peer review. Not just a couple of reviewers saying that your work is alright or includes something of use, but other scientists, many more eyes focused on your work, pointing out the flaws in it. This is vital, and that, I guess, is why I have to apologise. In my complaining, I fell into the same sensationalist idea that the paper had probably got it fairly reasonably okay, when I should have perhaps waited a bit longer. I still think the brunt of my rant is good. It does serve to highlight the caution of sensational reporting that I was complaining about with saying that the black hole was impossible. It does science no good to have stories of scientists finding things claimed as impossible or needing a radical rethink to our understanding of astronomy, then seeing them disappear as just errors or not being impossible. But I should have done better, and for that I apologise. I'll be away from the weekly astronomy videos till after Christmas, so until then, goodbye.